Hi guys, hope all of us are doing fine. My name is Ernest and I'd like to welcome each and every one of us to my channel of Ernest Sciences and Mathematics TV channel. In our discussion today, I'm going to look at a concept of conservation of momentum. And of course, this is going to be forming a crucial part of us understanding the various aspects that we're going to have a look at, particularly having this specific idea of conservation. And in our previous video, we have talked about various range of aspects ranging from energy, electrical charge, and even electric current, which are going to be obeying this idea of conservation. Now, in a sense, I basically mentioned that we are going to have this aspect of conservation whereby in just a general description, we are going to say that whatever goes in, of course, is going to come out. And in this case, we are going to look at various quantities which we have particularly looked at among whose examples I've mentioned. And this include, of course, the concept of energy, electrical charge, and electrical current. Now, in our previous discussion, of course, on the concept of the Kirchhoff's law, I mentioned that the input of Gustav Kirchhoff gave us one of the laws which we are going to, of course, be relying on in trying to find some electric current at a junction. And that gave us, of course, one of the examples which I've just mentioned for a conservation of electrical charge. Now, in this particular case, we're going to look at the concept of momentum in a way of describing the external forces. And we have decided that for us to establish this specific aspect of course, of equilibrium, we had considered that the sum of external forces are going to be equivalent to 0. And therefore, that is going to imply that the rate of change of momentum is going to be given as 0. So in this case, just given that we can illustrate the force which is going to be involved by a particle given by the summation, or rather this is going to be given in terms of delta mv all over delta t. And this basically implies the rate of change of momentum, which we can give in terms of dp all over dt. Remember that we are going to give momentum in terms of the product of mass and velocity. And therefore, in this particular case, whenever we're going to talk about different types of forces which are going to be involved in this particular case, particularly for external forces, they are going to sum up to 0. And therefore, this specific rate of change of momentum in this way is going to be, of course, 0. And this is going to be, of course, in a way giving us an impression of the conservation of this specific aspect of momentum. And therefore, we're going to see that the total momentum which is going to be involved before and after are going to be, of course, the same. Now we are going to look at this one using this specific aspect of the total, of course, the total aspects of a system whereby momentum can only be changed by external forces. And as we said, this is going to be only a consideration of this specific aspect of course, these external forces which we're going to be considering for a particular particle. Now, in a sense, we are going to look at this specific, of course, kind of question set, where we're going to consider this object which is going to be, of course, released from the nozzle. So this is going to be a bullet. Now, this bullet is going to be fired to a particular target, which is going to be situated at a particular point on a platform that is a low friction wheel kind of setting. And this bullet is going to be hitting this specific, of course, object. Now, we're going to consider the momentum before this specific object hits this target. And that is going to be creating for us the initial momentum of this traveling object. And therefore, consider the evaluation of that one with the impact that is going to be having with this specific target. Now, we have been given this particular information for the mass of the bullet, which is m1. And of course, we're going to see that the mass of the target is 4 kilograms, given as m2. The velocity with which the combined target is going to be embedded in this specific target. They are going to move together at a velocity of 5 meters per second. And for us, we are required to find, of course, the initial velocity, which is going to be the velocity of this specific bullet which has been fired. Now, the concept of conservation of momentum, whose case is going to be given as one of the application cases which I've just given on my right side of the board, is going to be widely applicable in various areas whereby we're going to come across, especially the concept of collisions. and some of the aspects of explosions which are mentioned in our previous video, especially on the concept of launching of space shuttles and rockets. Now, of course, this is going to be assisting us in trying to evaluate the various aspects of motion and also the energy involved, especially during launch and perhaps during the course of motion. Now, I'm going to summarize this specific, of course, concept of the conservation of momentum so that we can go ahead and try to do this evaluation and see what are some of the descriptions that we can associate with it. Now, we can give this one in terms of a summary whereby we're going to have the law of conservation of momentum stated that when two or more objects, I just give this one in summary form, when two or more objects, hope my writing is legible, interact, their total momentum remains, so this is R remains constant, providing no external force is acting on them. So this is going to be acting, provided no external force is acting on them. So in a summary form, this is going to be providing for us the, of course, the law of conservation of momentum, which is going to be given in terms of when two or more objects interact, their total momentum remains constant, provided no external force is going to act or is acting on them. So in this case, we are going to have this specific first and second objects interacting. And in this case, we are assuming that there's no external force which is going to act on them. And therefore, we had just mentioned that this is going to be a setup based on a law of friction wheel, of course, which is going to be countering that force of friction which we had discussed in our previous videos. Now, in this case, we can give this one in terms of total momentum before. So let's assume that they are going to collide. So total momentum before collision or impact is equivalent to the total momentum after impact. So this is going to be relevant in most of our applications whereby we're going to consider this specific momentum as, of course, a product of those two specific quantities for mass and velocity. And therefore, in our case here, we are going to consider where we are going to have an evaluation whereby we are going to have the product of course, mass and velocity of the bullet is equivalent to the product of mass and velocity of that specific target. But as we said, this specific target is going to be, the bullet is going to be embedded in this target, and therefore we're going to consider a case of having the same velocity but different masses. Now in this case, we can give this relationship for momentum as the mass of the bullet given as m1 times the velocity plus the mass of the target given as m2 times the velocity. But remember, in this case, this is going to be a specific target which is going to be at rest. Therefore, its velocity is going to be considered to be, basically its velocity is 0 given as such. And this is going to be the momentum of the target and the momentum of the momentum of the bullet and the momentum of the target are going to be, so in this case, this is going to be forming our bullet, and this is going to be forming our target with a condition that this one is at rest, and therefore the velocity is 0. So after impact, we're going to see that basically the velocity with which they are going to move together is going to be 5.0 meters per second. And therefore, we're going to expect this one to be having a sum of their masses, but a constant velocity of v given as such. So in this case, this is going to be assisting us evaluate this aspect of u given as the initial velocity, whereby we're going to have the mass of the bullet, in this case, given as 100 grams. So this is equivalent to 0.1 kilograms times the velocity of this bullet, which is given in terms of u. And this is going to be a sum with this specific product of mass and the velocity of the target, which is 0. And this case, we're going to have the other side giving us the sum of the mass of the bullet times the mass of this specific target, which is 4 kilograms, and this is going to be times the velocity, which is 5.0 meters per second, given as that one. So we are going to have u as our subject of this formula, and therefore this is going to be given in terms of this specific ratio of 0.1, and then we're going to have this one times of course 5.1, or just 5.0 meters per second, given as such, and this is going to be giving us a value of u equivalent to 205 meters per second. So this basically is going to be giving us the velocity of the bullet, given us the initial velocity of just the velocity u of the bullet whenever it was going to be, of course, traveling before impact with this specific kind of a target. So this is one of the ways we're going to be applying the law of conservation of momentum, and this is going to be a vital, of course, consideration that we're going to see in a various range of our videos. So that is it for now, guys. By God, please, we'll catch us in our next video.